Yes. So, in lecture number 18, we are going to focus on the furrow irrigation hydraulics again. So, previously by knowing the advanced curve, we will be able to estimate the infiltration characteristics like Kosteiko infiltration parameters for a particular field soil. But in this lecture, so we are going to see the procedure, whole procedure to find out the advanced curve by knowing the infiltration parameters. So, it is kind of a reverse in the previously what we did. So, we know the advanced curve and we estimated the infiltration parameters. So, now by knowing the infiltration parameters of particular field, so how to estimate, how to simulate the advanced curve. Okay. So, in this, so this is a flow chart clearly showing, like you have seen the input data required here, Q naught, S naught slope, roughness coefficient, shape parameters and Z required. So, this is what we expect in the subsurface. So, this is a cumulative infiltration we expect for a particular crop, and A, K, F naught infiltration parameters. So, because the infiltration parameters are known. So, our task here is, so in this situation, so what would be the advance look like, how the advance is going to move from head end to field end knowing the infiltration parameters. So, the first step is we again focus on volume balance equation. Okay. So, A naught which is equal to Q naught n into 60 rho 1 S naught 0.5 1 by rho 2. So, A naught flow area at field inlet. So, then initial guess of R between so R here is similar to the B. So, B is the advance, the waterfront advance power advance coefficient. If you remember, x is equal to p t power b, right. So, here R is please note that this R we are showing is equal to b, the same as b. So, here and then sigma z, if you remember the key for sigma z. So, this is the equation A plus R into 1 minus A plus 1 and 1 plus A plus 1 plus R. And sigma s. So, this is tagged to the F naught in the volume balance equation, that is 1 by 1 plus R. So, initial estimate. So, in this case what happened? So, T L. So, and before even doing that, so this when you have the implicit functions, that means, so the function I mean the independent variable is implicit. Okay. So, the whole function is implicit. So, in that case, so you have to use, and you cannot solve the equation directly, you can use some numerical techniques like Newton-Rapson technique. So, suppose you have a function f x, okay, and so there is initial guess x naught. So, the new guess x 1 is equal to x naught minus f of x by f dash x. Okay. So, this is Newton-Rapson technique. So, every time you get some initial x naughts is initial guess x naught, okay, and find out what is f x and what is f dash x naught, okay, f x and f dash x naught and x naught, and you get x 1. Okay. Now, you check whether this x 1 is close to x naught or not. Okay. So, if they are very close, like you are expecting x naught minus x 1, let us say ampersand less than or equal 0.001, this is tolerance level. So, if you if this x naught is very close to x 1 or x 1 is very close to x naught, then you can stop the process. Otherwise, again this x naught needs to be have a next initial guess. So, that would be like x naught is equal to x 1. Now, you get x 1 and put the x 1 here and x 1 here, okay, and find out this function values, and this is x 1 okay, x naught equal x 1. So, now you get new x 1 and compare with the previous x 1. So, similarly, so every iteration you will get the new x 1 and this will be compared with the previous x 1. If these two x 1 and x naught are very close, then you stop the iteration process and the guess will be the right answer for the right solution. So, this is finding out the solution in case of implicit functions. So, here in our case this is an implicit function. If you look at this, so basically we are looking for the advanced functions, advanced curves, that is A. Okay. So, and then there is and the time also is the unknown function. So, time and A. So, here R or B, so we vary in between 0.3 to 0.9. So, sigma z, so which has R which is unknown, okay, and here also R which is unknown. So, what we do here, first T L, okay. So, T L which is equal to T 1 equal 5 into A naught into L. So, this is initial guess. You can also use any initial guess, but in order to reduce the number of iterations. So, the T L which is equal to 5 A naught into L by Q naught. Okay. So, then T 2 is equal to, as I mentioned. So, you get this is the new T and this is initial T, and this is, if you remember the volume balance equation. So, this supposed to be a minus. Okay. So, volume balance equation Q naught into T is equal to sigma y A naught into x plus, okay, and sigma z k T power A plus f naught into T into x by 1 plus b. Okay. Right. So, this is equation. So, let us say if this is a function x, what happened? This is negative and this is again negative, okay, all negative. So, the same thing here, Q naught T 1 minus 0.77 A naught into L minus sigma z into k T power L minus sigma dash, that is 1 by n, f naught into T 1 into L. Okay. So, this is the function f of x. So, the next is the bottom one is f dash x, right, function f dash x. So, here the x is the time. So, we are differentiating with respect to time, So, Q naught minus everything you get. So, then for a particular initial guess, substitute T 1 and this, and you get T 2, and now you see whether T 2 is close to T 1 or not. If it is not close, again you go back to the you update the T 1 with T 2, right, and do the iterations as long as T 1 is almost equal to T 1, that T 2, that means very close. So, then you will get what? You will get by the way, we are targeting the advance point at the field end here, right, at the field end. So, here L into T, So, that is why we put x, we substituted x as L, right, remember L. So, then the next, So, the next continuing this. So, if they are close, T 1 and T 2 are very close, okay. So, then you got the advance point at the field end. So, now next the advance point at the middle point, okay, or the at L by 2, at L by 2, okay. So, we will follow the same procedure, for L by 2, x equal to L by 2, okay, and then same T 1 T 2. So, one at the field end, the other one is at the x by 2, L and L by 2. So, we found T here and we want to find T here by substituting x is equal to L by 2. we follow the same procedure, same Newton-Rapson technique here, and same iteration procedure, and finally you get T 2 here. I mean this is let us say T 0.5. So, 1 T at the end and 1 T at the 0.5 L. You got two advanced points you got. And now, the find out the B value. Okay. So, you started initially by assuming B value like 3 or something, and found out that particular B value, what are the two advanced points. Now, you calculate back, okay, with this same B, okay, by ln by 2 ln T L by. So, this is ln x 2 by x 1 divided by ln T 1 by T 2. Okay. So, then find out the new B. So, now check whether this B is close to what the initial guess B. Okay. So, if they are not close, and again change B and find out T 0.5 and T L, okay, and estimate B. Now, again compare, if they are not, if they are close, and you are done, and finally, you will get the advance point at the field end, advance point in the middle point, and R value. R is the coefficient. Okay. So, you get x 1 T 1, x 2 T 2, okay, and also you get the advance I mean the power advance coefficient. Okay. So, this is all the procedure for finding out the advance points. Okay. So, the next is computation of intake opportunity time. So, this is very important to find out what is the cutoff time. Okay. So, here basically intake opportunity time tau required. So, that is the Z required. So, in any problem for a particular crop, so we expect you know 10 centimeter or even 20 centimeter. So, that is the Z requirement. So, Z required here we are targeting to the field end. Suppose this is the advance and this is infiltration, right, this is infiltration. So, at the field end we expect, let us say this is Z required. Okay. So, Z required, we do expect the field end. Okay. So, that is called Z required. We are expecting the infiltration, the vertical infiltration reaching the Z required point. Okay. So, that one, and then the time can be obtained from modified Koshakov equation using Newton-Rapson procedure, as I explained the same. So, if you remember that, so this is the function of tau and function, a derivative function, and this is a new guess and the I mean initial guess and new guess, the same thing. So, x 1 equal to x naught minus f of x naught by f dash x naught. So, similar to that. So, tau required will be estimated. So, where, so this is Z required. So, we know the equation, right. So, Z required or Z equal to, let us say Z is equal to, okay, sorry, k t power or tau power with this opportunity time and f naught into tau. Okay. So, same equation. So, if this is the function, what happened, f tau is equal to Z minus k tau power a minus f naught into tau. So, that same thing you get here. Okay. And then f dash. So, differentiating with respect to time, you get this. So, knowing this f and f dash, substitute it here for the initial guess and find the new tau. Okay. If the tau is not close to the initial tau, so then again you have to update the tau and find the function values and redo the iterations, and finally you get the solution tau. Okay. So, that is infiltration opportunity time you get. So, once you get the T required, that is infiltration opportunity time. So, the time of cutoff is equal infiltration opportunity time plus the advance time. So, what happened? So, this waterfront advanced to this is the field length L. Okay, this is the if this is the field length L. So, when waterfront reaches here, the time is T L. Okay. So, then if this is Z required, if this is Z required, so at this point when it reaches the field end, so Z required is almost this is 0. Okay. So, now we have to deliver water until this vertical infiltration reaches to Z required. Okay. So, that is infiltration time, that is tau required. Okay, tau required. So, from point 1 this point to this point, the time taken is tau required. Okay. So, that much time you need to irrigate. Okay. So, that T L plus the extra time. So, that will be the cutoff time. Okay. This is cutoff time. So, the value of Q naught should be adjusted so that the number of sets an integer number. So, we are going to see these calculations in the next example. Okay. So, here basically in the design parameters in the simulation purpose, we required Koschekow-Lewis parameters, this one, and field length, width, okay, furrow spacing, the slope, shape parameters, Manning's roughness coefficient, Z required for a particular crop, and Q the capacity, the total water source, and Q naught is the flow per unit width. So, I mean for one set of Q naught, and T the duration, NF is number of furrows. So, this information is at least required for designing or simulating the furrow irrigation system. Okay, so this is the design procedure. I will go a little quick because some of things I have already covered in the flow chart. So, if you see this, so the design of a free drainage or a furrow irrigation system. So, that means the tail end is free. Okay. So, the tail end is free in the sense there is no dike over here. So, water is flowing directly and causing the runoff at the field end. Okay. So, in this case first thing is they collect the following required field data, field characteristics. So, all field information like length, width, area, slope and Manning's n, soil characteristics like texture, water holding capacity and all other things, crop, right, in the type of crop, design irrigation requirement, this is very important, and water supply. So, what is the total water supply available, and furrow characteristics like spacing, bed to bed spacing, shape, okay, and shape parameters. So, this is the basic field data required, and then so next is the determine the furrow geometric parameters using the equations explained, right, and knowing the furrow parameters like top width, bottom width, okay, and depths, corresponding depths. You can find out furrow geometric parameters. Okay. So, that is rho 1 and rho 2 you will find out, and compute the intake opportunity time. So, I just explained a few slides back. So, how to estimate Z required, okay, and then compute the maximum furrow discharge, that is Q max. So, this is the based on the non erosive flow velocities, that for soil to soil it is different. Okay. So, that is the for a particular soil type. So, what would be the maximum flow rate, so that that flow rate does not cause any erosion. So, that is the meaning of this. And if you see this table, it clearly shows the velocity, okay, which is non erosive velocities here for different soil types, and the velocities we expect in different soil types for non erosive. So, Q max can be estimated using Manning's roughness equation, Manning's equation, and then the fifth step is to find out the discharge, select the furrow discharge Q naught near to Q max. So, what happened, I mean this Q naught needs to be found out. You find out Q max and find out Q naught which is nearer to Q max, okay, for the particular the field, furrow field, which results in the integer number of furrow sets. So, here assume our thing is NS is the number of sets. So, the number of sets is equal to number of furrows in Q naught by total capacity. So, that is number of sets. So, you have this much capacity, and this is the flow rate for each furrow, and this is the total flow rate, and you get number of sets, and number of furrows per set is number of furrows plus number of sets will give the number of furrows per set, number of furrow sets. So, number of furrow sets is equal to number of furrows and number of sets. Okay. So, here this is number of furrow sets is equal to number of furrows by number of sets. Okay. Number of furrows by number of sets will give the number of furrow sets. Okay. So, then next is calculate the cross sectional area. Okay. So, this is the equation we already know. So, Q naught which is close to Q max, and A naught is knowing the furrow shape parameters and other values n and S naught, you can find out A naught, and V max is equal to Q naught by A naught. Now, you check whether V max is really matching with the non-erosive velocity or not. So, if not, again you have to change Q naught or increase or decrease Q naught. So, that V max should be non-erosive flow rate. Okay. And seventh step, so here from assume an initial value of advance exponent, that is R, which is equal to B advance. So, from here onwards we will follow the flow chart we just explained before, right. So, first this is the initial guess, that is B equal to 0.5. So, for 0.5 we are going to find out sigma z and find out time at the advance point, I mean field end, time at the middle of the field, okay, and then find back the B value. Okay. If the B value is close to what assumed values, so then that is fine, otherwise you have to change B value and redo or recalculate the final advance point and a middle advance point. Okay. So, as long as the B values are close, so then you get the B value as well as the two advance points. Okay. So, the whole procedure from now on will explain the flow chart. Okay. So, the everything is so here you can go through compute the necessary flow advance L distance. So, this is all the flow chart. Okay. So, everything this is follows the flow chart explained in the first slide. Okay. And then yeah, even this one also. Okay. So, this everything up to this follows. Finally, you get you find out you calculate R value, and now this R value will be compared or B value will be compared with the initial guess value. Okay. And then compute the cutoff time. So, the previous flow chart will give the T L, okay, and then tau required, this is again using Newton-Rapson technique. So, this is the cutoff time. So, this cutoff time is really required to match the Z required, okay, infiltration time. So, now the 14th step, compute the application efficiency. So, once this is done, we do the application efficiency. So, here we assume that the resistance and depletion phases are I mean 0, I mean there is no, we neglect the depletion and resistance phases in furrow irrigation for volume balance cases. So, now E A, which is application efficiency. So, Z required into L. So, suppose, so this is Z required and this is L, right. So, this amount of water is being used for infiltrating the surface out of Q naught into TCO. Okay. So, this flow rate you continuously irrigated up to this many hours. So, this is the total volume. Out of this total volume, so this much is really applied or stored in the root zone. So, this is the application efficiency. Okay. And then application efficiency should be maximized considering the different values of furrow inflow rate subject to the limitation on erosion velocity. So, here for each Q naught, for each Q naught, and you are going to, and each Q naught, so find out what are the number of furrows and number of sets, number of sets and number of furrows, okay, and corresponding E A, that is application efficiency. Okay. So, similarly you get another Q and find out this and find out this, and similarly you during this process you will be knowing for which set of like number of furrows and set and the corresponding flow rate you get maximum efficiency. So, that I mean computationally it is easy, manually it is I mean tedious. Okay. So, at least 3 Q naught values should be tried in order to identify a value that maximize E A. Okay. And same procedure to be repeated considering the representative values for infiltration parameters lateral irrigation during the season. So, this is the first irrigation you are considering. For first irrigation, so you got Q naught, you got you know the number of sets to be irrigated and number of furrows to be irrigated, and then the other parameters like you know advance point, time of cutoff and irrigation efficiencies. So, similarly, the same procedure you can use it for the next I mean following subsequent irrigations, because during season you have number of irrigations, is not it. So, the first irrigation and this maybe you know the sometimes you get 22 you know 22 irrigations, 22 irrigations in a season we expect, but all number of irrigation depends on the crop. Okay. So, here yeah, so that is all procedure. So, now the actual problem here I will go again quickly. So, these are the parameters explained before. So, these parameters are required for designing purpose of soil type and furrow spacing, the Z required is given and infiltration parameters rho 1 rho 2 and supply duration and the total available supply Q is given. So, with these parameters let us design for irrigation system. Okay. So, as I said the first thing is find out what is tau required by knowing the Z required. So, this using the Newton-Rapson technique on modified Kostyakov equations. So, a new value. So, you follow this equation, follow the procedure explained. Okay. So, finally, what happened you get tau value which satisfies you know the values. Okay. So, that will be about 116.044 minute, right. tau required. So, that means, so once it is reaching the advance and in order to meet the Z required, so it needs to be irrigated for 116.04 minute. So, then only at the tail end the waterfront is going to reach the Z required. Okay. So, this is one task is done. So, the next task is to find out what is Q naught, okay. Q naught and the number of furrows. So, Q max for maximum non-erosive velocity, velocity 8 meter per minute. So, the Q max using the velocity, you just this is from table, find out Q max by using Newton Rapson, by using what you call this Manning's equation, okay, and you get Q max is this. And then next, the third step is to find out the number of furrows and number of sets. Okay. So, here the equations are used. So, number of furrows, this is the total width divided by the distance between the two furrows. So, that will give total 1000 furrows for whole width, right. The whole width, it requires 1000 furrows, right. Width is given and spacing between the two furrows given. So, that is 1000 furrows, and number of sets, that is the number of furrows and Q naught divided by total capacity. So, that is 16.66 furrows per set. So, each set will have 16.66 and number of furrow sets, number of furrow by number of sets. So, total 60 sets. Okay. So, total number 1000 furrows, 60 sets, 16.66 sets. So, furrows. So, this is like a real number, we are looking for integer. So, that is the reason what we did. So, we follow the same procedure by changing the sets. Okay. So, 10 sets, 8 sets, 5 sets, 4 sets, 2 sets, 1 set, and the combination. So, this total, multiplying these two should give 1000, is not it. So, multiplying these two will give 1000. So, like that. So, all will give 1000 furrows, but the sets and number of furrows per set are different. So, with these combinations we find what is Q naught values, okay. And the first in this example, let us take 0.0450, which is close to your non-erosive flow discharge, that is 0.07 it seems. If we go back, sorry, again anyway. So, if we go back to 0.07, which is within less than the non-erosive flow rate. Okay. Now, that way, so selecting the Q naught value, find out A naught. Okay. So, then and then find out what is V max. Okay. So, if the V max, let us check whether the V max is less than the maximum permissible velocity or not. So, once it is less than maximum permissible velocity, in this case it is less. So, still we are good, it seems. So, then so this whole after, so up to this what we found the Q naught and number of furrows per set, number of sets. Okay. So, that is we got, and then after that, and we are going to find out what are the x as what is T L, ln T L and 0.5 ln T 0.5 L. Okay. That means two advance points using the flow chart we explained. So, this whole procedure will explain that. Okay. So, I do not want to repeat. So, from here onwards, we found compute the time flow advance T L. Okay. So, then again compute. So, once you get two advanced points, okay, then for a particular and then you find out the new r, fine, and then see whether the new r is close to what the initial r. So, initial r was 0.5 and the new r was 0.5048. So, that means they are very close and the corresponding advanced points are can be accepted in this. Okay. So, you got advanced points, okay, you got advanced points and you got B at the end of the flow chart or at the end of the iterations. So, knowing the advance time and then tau required, which was already estimated, and then you can find out TCO. So, the TCO which is cutoff time, I mean from delivery point to you have to cut down the discharge at 139.79. So, that the field end, so the infiltration depth will reach to the Z required, okay. And then find out the efficiency. Once it is done, so find out the efficiency using this equation and check the water available the duration complete 10 sets. So, you have like you have for one set is 139.78, for 10 sets they multiply with 10, you get total 23.29 hours in order to irrigate the entire field, okay. Is the number of sets, like one set is done. So, 139.78 for this set and then irrigate the next set and next set and next set. So, the total, if you do not have any I mean rest time between the sets, it will be 23.29 hours and irrigation is complete within a duration of water supply, okay. So, repeat step number 4 to 13. So, step number 4 to 13 by changing the Q values. So, for each Q you have to change the values, change these steps to be followed, okay. And finally, what happens, you get for each set or each flow rate, okay. So, you get efficiency, you get cutoff time, you get everything. So, you find out then from the table. So, then you can tabulate that, you can tabulate the whole thing, like you get Q naught, what is time of cutoff, what is EA, right, application efficiency, okay. And also the sets, furrow sets and the number of furrows and number of sets, okay. So, now you have to pick which one is the maximum efficient combination. So, you pick that and follow, and that is the perfect design. So, here the maximum EA was obtained for furrow inflow rate of this 0.036, that is 8 sets and 125 furrows per set, and TCO cutoff time is 160.86 minutes. This should be sufficient to irrigate whole field. So, this completes the whole irrigation design procedure for that, okay. And so, this is all for this lecture. So, in this lecture basically we focused on how to estimate the advanced times by knowing the infiltration parameters. Okay. So, in this case what happens, so that is the one thing. Suppose in the design problem, so these some of the input parameters are given. So, knowing the input parameters, so in furrow irrigation design, so the main target is to find out the flow rate, particular flow rate that is sufficient to enough to irrigate the whole field by making different sets, or and also that would be enough to give a maximum application efficiency. Okay. So, this is all, and we have, so the main key computational in the procedure we used in Newton Rapson technique, and we will be using this technique throughout I mean, and even in drainage case also. So, so remember the procedure. So, in Newton-Rapson technique, so any implicit function can be solved or finding the solution using this Newton-Rapson procedure. Okay. Yeah, thank you so much.